So, welcome to our second session on airborne wind energy for today. So, this one will be the second last session for today. The one after lunch is the last one. I thought there were two, but there is only one after lunch. So, we do have still some presentations to do now. So, first speaker for this session is Dr. Mac Gauner of DTU, Denmark. Very interesting presentation about the accuracy of lifting line models, and that's your specialty, and we also collaborate frequently on this via master thesis projects, which I find very interesting sessions. So I'm curious to learn what you have to say.
Thanks a lot. Hope you can hear me. So I'll be talking about lifting line methods and details, the finer details, and when you want to implement stuff like this. We were very anxious to hear about it after 4 hard days of equations and hard drinking and conference dinners. So I hope you're up for 30 slides in 10 minutes. There's an outline, and I will be a little bit vague. I will not have time to go into all the details. I'll get the main points. And I'll try to focus on some take-home messages. So that's an outline. And so lifting line, why would that be nice? So I come from conventional wind energy, and there we have all kinds of models ranging from 100-year-old blade element momentum stuff that you would think should be dead by now, and then we have all the fancy methods that can do all kinds of detailed stuff, but there's a lot of focus still on the simple models. Simple and fast, because the wind field is unpredictable, it's turbulent, and you need to know how your turbine reacts, and you cannot always do the heavy calculations. So speed is very important. And if it performs pretty well, then you're well off. The pros for this kind of model is that it's very fast, potentially. You can use 2D data to input into it, so it's not. It's based on potential flow, but it's not. Doesn't need to go. Lift doesn't need going up. So you can use it for optimization. You can model the key behavior of geometry, of sweep, dihedral, unsteady situations. Maybe if you do it right. Yeah. And the cons is that there's some iffy things when you start going into, you start using airfoil data that go into stall. There's some numerical issues when it's hard to figure out that part. So I'll focus on the stuff in this red box here. So you split the problem into an inner problem and outer problem. And the outer problem is the 3D system. So if you go very far from, let's say, a wind turbine, is like 3 sticks with forces on, that's the wings. And if you go, you can think of that as a grid of the wake behind, could look something like this. And then the inner problem is the 2D section, where if you go into it, look at it, you have a leading edge, trailing edge, pressures on that. And then we split these sides, or these domains. So, yeah, so these two parts have to be coupled, and the whole trickiness in the method lies in this coupling, actually. So to understand how to couple it from like a fundamental point of view, it's a good thing just to start looking at the inner problem first. And I've been working a lot with unsteady thin airfoil stuff, so I looked at that. And all the devil is in the details. And how you do that thin airfoil theory, unsteady stuff, is like you have a reference setup with a constant wind speed, and then you have an airfoil that moves around. It has translation and rotation. So what the airfoil feels is there's different velocities at different locations along the core. So this is the component perpendicular to the airfoil, and then there's also a free stream velocity, or like the other component of it. But the thing is that along the chord of it, it experiences different things along it. And the key key thing here is when you do all this thin airfoil stuff, then there's three important things that pop up. One is that the angle of attack, where you measure, you should measure to look up the lift and drag data. That should be evaluated at the three-quarter point here. And the angle of attack, or the flow direction, relative flow direction, that determines in what direction you put the lift and drag on. Drag is in the direction of the flow at this evaluation point, but there you need to use the directions of the flow at the one-quarter point. And the velocities I'm talking about is the velocities that the airfoil, that you feel at the location of the airfoil, but it doesn't actually include the disturbance of the airfoil or its own wake, the two-way wake. So the driver of the inner thin airfoil problem does not include the disturbances of the airfoil itself. You think of that as an engine, you put something in, you get some forces out. So that's to keep in the back of the mind when doing the lifting line stuff. So from this last point, since you are not supposed to include the velocities that the 2D vortex system induces, the right velocity to look at when you do the lifting line stuff is the total 3D induced velocity from the system minus the local 2D bound one, because that's already included in the thin airfoil model itself. So this is the velocity that the inner 2D section should be using for this to be consistent. So then you evaluate that difference velocity at the three-quarter point there at the cross. Let's say this is the interesting section, and then to get the important velocities that drives the behavior of this section, you need to subtract the influence of the green vortex, the 2D vortex there for that section. And this is the way. If you do that, then I'm happy, because then it corresponds to what thin airfoil theory says. So, and then there's one more thing. Let's say you have a wing like this with a lot of sweep. Then there's one more free parameter, because now I say that from a cross-flow principle, it's you always use directions perpendicular to the span, and I define the span like the quarter chord, because that's where the action point of the force is usually allocated. So I'm taking the decision just to say, well, the bound vortex comes, the total force vortex horseshoes comes from infinity, goes to the trailing edge, goes in a direction perpendicular to the span, to the quarter chord, and then goes back like that. So this is a free choice that I've made, and I made that because of the cross-flow principle. You can't make a very long, like infinitely long 2D wing if you turn that, you can't get anything right until before you realize that you have to use the direction perpendicular to the span. So that's why I do this, and I'll impose this in my solution and see how it works. But if I do that like this, if I put it like this, then now this vorticity that goes in this bound direction here, there will be a force on it, because now it's not aligned with the main flow direction. So I need to include that part of the force in my solution. So this is the new thing in this way of looking at it, along with the explanation of 3D minus 2D. So these forces, the forces that act on these straight bound vorticity, you can see them here. It's maybe a little bit tricky. You're looking from the wing, it's like half from behind. So there's the green things are the forces that act on this part of the bound vortex. The blue things are the forces that act on the other part of the vortex. So there's an extra contribution to the forces if you think of it like this. Okay. I want to compare to something. My truth will then be something I know well. I'm doing vortex lattice solution of the same geometry. And then vortex lattice corresponds to it. If I do that in 2D, I get an an implicit lift polar. So if I'm comparing towards this lattice method, I input in the lifting line method a 2 pi alpha lift slope and 0 drag. And then I should be able to compare the results. And in order not to confuse myself, I'll be looking at comparisons of lift coefficient and not really drag, because if my lift is a little bit different, the drag varies a lot, because the drag varies with lift squared. Induced drag varies like that. So I'll be comparing lift coefficients of the different implementations and then the span efficiency, defined like this. And then I can see whether the induced drag I get, how that compares to lift, because otherwise I'm confusing myself. And I'm looking at a number of cases, and I'll be running through them, and someone needs to tell me when I only have 2 minutes left because I have a lot of results. I'm looking at 4 different implementations of a lifting line. The one I just suggested, the one that corresponds to what a lot of people do when they read the original work by Prandtl. If you use now instead the more correct evaluation point at the 3/4, but don't include the bound vorticity, and evaluate also the drag from the on the kite using that angle. And then there's the Rannenberg one, that is vortex step method. And what you see here in all these tables here is like VLM results, that's the reference, that's the one that I think we should believe. And that's the one that the other methods want to look like. So this is then the CL, and then this is the difference in percent. So these are pretty close. This is a straight elliptic wing, aspect ratio high, standard angle of attack. That's the Oswald efficiency for an elliptic wing of high aspect ratio. This solution gives, the analytical solution of that gives 1. So it looks like it's implemented more or less correct. And the high aspect ratio case, we get the same numbers here for almost everything over here. But this is using the drag that you look at when you look at what are the forces that I evaluate on my blade. And this is the Oswald efficiency that when I use a drag I get from a far field analysis. And the catch here is that the far field analysis stuff you can only do when you have a steady uniform inflow case, which is never the case for a kite. So this is something that you can use for straight line conditions. This is very close to 1 all of them, so that's happy. But you see here that if you use these 2 methods and use the way I've implemented it here at least, then you get something pretty wrong for the drag. So if you use these methods, you have to use the far field methods to get the drag right. So that's not good. And these are local loads. This is local lift along the span and local induced drag along the span. And here you see why one of the numbers here was completely off. If you evaluate the drag from profile polars and putting the lift on with a velocity as predicted in the Rannenberg, here you get an induced drag that is way off. So here you have to use actually the far field approach. So I try to look at different cases just to see when things go wrong in the different models, or if they go right in the model that I'm working with here. Now, low aspect ratio, and actually my model here is very close to the VLM with this regarded truth. Now, this model down here starts behaving badly because I'm evaluating at a wrong point. I'm evaluating induced velocities here and not here as I'm supposed to according to thin airfoil theory. And you can see that this messes with the results here. These 2 methods where you evaluate at the 3/4 chord velocity and regard that velocity as the reference direction that you put the forces on, you get the drag completely wrong. And again, VLM truth is black. The thing I claim to be a good idea is blue, and it looks good. Rectangular wing, more or less the same conclusion. High aspect ratio. Blue and black look really good. Low aspect ratio, same story. Anhedral. Now we bend it like a kite. Then what? Well, this is still, this method is not good. These numbers show that when you evaluate the forces on the blade, we're doing good, and they agree with the numbers from the Trefftz analysis, so we're good. So it's pretty nice. These results still give good results for lift and drag if you use the far-field approach, but if you are not flying straight or doing maneuvers, you can't do that. Again? Yeah. Now you sweep it. That's a little bit numerically more tricky. This is where you have these new forces coming into the game. It does look kind of good, I would say. Now these and these disagree a little bit. I speculated a bit why that is. Maybe that's because the wake is not force-free when you do the far-field approach. You also include the forces on the wake, actually. Again, the new method, blue and black, close, happy, happy. What is that? Swept. Swept and bent. Again, good. Good. Now you take the anhedral wing and make a maneuver. And here, what we see is that these results are completely ridiculous in terms of what you usually see. Oswald efficiencies for the ideal elliptic wing is 1. Now we have something that is way, way better. And that's of course because now we are making a maneuver, so actually we're putting energy into the system. And that's why the drag can go also below 0. But that's just so if you take this situation and try to analyze the wake from that, with the Trefftz analysis you get something that's way off. And this is just to show you cannot use Trefftz analysis when you have a maneuvering thing. But still, overall, the new implementation of the lifting line seems to be nice. Black and blue. Observations, it agrees well. I think it's a good explanation. Either for tricky geometries, swept wings, bent wings, unsteady maneuvering. This shows that the assumption of this chord-wise trail vorticity is probably not so bad. Because the VLM don't care about that. It just solves the problem. So VLM can be considered the truth. Conclusions. Thin airfoil theory gives good hints about how to implement lifting lines. You have to include the span, or the chord-wise, span perpendicular power vorticity, and have the forces from it to get it exactly right when you have that swept wing. Then you can calculate all sorts of stuff. You can't use Trefftz-plane analysis for the general case, where the kite is moving. Good agreement. And if you just make lifting line implementations that differ a little bit, you can get very different results. So when people say, we have made a simulation with our lifting line code, we're good, that's not necessarily the case. So that's this. And so this is the bring home message. So further work would be trying to tackle what the tricky stuff when you have stall airflow data. And that's probably finishes what I have to say.
Thank you for this interesting presentation. Are there questions? Yeah.
Thank you very much, Mac. Very lovely. I was wondering, so you were talking about that the details matter a lot, right?
Yes.
The depth was really in the details. So will you be publishing your approach to how we should tackle these details?
Yes.
It would be good to clarify.
Yes, and this is brand new stuff. I programmed like a crazy guy every night here, so please don't publish it before me. So we'll go home and talk with Georg and Ang, and then we'll get on cracking.
Great, I'm really looking forward. Thanks.
Just have to do a master project together with Mac, and then you will get some information. Are there any
other questions? I'm curious about the VLM simulations. What is the resolution in terms of elements, and did you do a sensitivity study
Yes.
about the number?
Yes. The sensitivity study of the VLM is that that converges nicer than the lifting line one. So VLM, I used, for these results, I used 81 points along the span, and I tried using 10 and 20 and got almost exactly the same number for a number of panels in the cold rise turbine. And to make sure that that resolution there was okay, I made a 2D version of that, so long Vortex, just to check that how to do the discretization in a smart way to use the least amount of energy like that. But really, that converges very, very fast. Thank you. And for the lifting line stuff, I used 160 points along the span, which is a lot. But actually, the most tricky part there is to get the tricky numerical case is the sweep, and to get the right drag from the on airfoil or on blade evaluation for the swept case. That's the tricky part. The rest is actually easy. And the new parts converts the forces from the new parts for the chord-wise bound vorticity on the airfoil, that converges fast. So it's actually the contribution on the quarter chord point in the case where you have sweep. That's the way where you have to take care of that discretization and things. Yeah.
Great. Thanks again, Mac, and I hope that you take some time off and publish this. Take off time from programming. Yeah, thanks.